In this video, we're going to learn about phasors and how we're going to use them in our circuits. So the idea is going to be that we have an AC voltage system, and we're going to start by looking at ones that are in terms of cosines. So the input voltage is going to be A cosine of some frequency omega t with some phase angle plus phi. And we're going to rewrite this as a phasor notation, capital X, as just A angle phi. It's basically the polar notation for complex numbers. And let me kind of point out what we're really doing here. So we have a voltage that is A cosine omega t plus phi. And that's what we have physically present in our circuit. That's what our voltage source is going to be providing. And we're going to pretend that it also has this second term that's imaginary, J A sine of omega t plus phi. And as long as we do our calculations and so on, as long as at the end of the day we get rid of the red part, we get rid of the imaginary part, then we'll have the right answer to the problem. So we're putting something in that we're eventually going to remove at the end to get our final answer. And it's going to turn out that putting this in is going to make our problems easier. So knowing Euler's identity, we can rewrite this as A e to the j times omega t plus phi, which we can then further break up as A e to the j phi times e to the j omega t here. And then that e to the j phi is the complex number in polar form A angle phi. And so what we're really doing is when we do our phasor notation and we take A cosine omega t plus phi and turn it into A angle phi, we are really just looking at the coefficient, the amplitude as a complex number here, having that as our phasor notation, and in some sense we're going to be hiding the e to the j omega t part. We'll see why and where it's going to come into play in a few minutes. On the other hand, what if we don't have a cosine? What if we have a sine? Well, that means we already have this kind of imaginary part but without the j, and it'd be a big hassle. But there's a better way to do it. We know from trigonometry class that if you have sine of an angle, it's the same as cosine of the angle minus 90. So we can go ahead and turn this b sine omega t plus theta into b cosine omega t plus theta minus 90 degrees, just by trig identities, nothing special. And then by phasor notation, that becomes b angle theta minus 90. And again, the e to the j omega t is kind of being hidden. So whether you start with a source that's either a cosine or a sine, we have a phasor notation to turn it into. You might say, well, what if I have some other source that's not cosine or sine? Well, there's a whole branch, a whole topic of mathematics of how to turn functions into cosines and sines. It's called Fourier Analysis. It's not something that we're going to be doing right now, but if you go further in circuit analysis, you will learn all about that and how to turn basically everything we deal with into sines and cosines. So now why in the world are we adding this j sine part? Why are we making it into phasors in the first place? It's because when you have your regular Ohm's law, and maybe I'll make it a little, not inductor here, let's do a resistor here. We have our regular Ohm's law. Then we know V equals IR, and that's a nice algebraic equation relating the voltage and the current. On the other hand, if we have a capacitor, we know that there is no nice algebraic equation relating them. Instead, we have a differential equation that I is equal to C dV dt. And as we saw in other videos, that meant that in order to solve a circuit, we had to write a differential equation out. And then we had to solve the differential equation, which As you get more and more complicated expressions, this gets worse and worse. But let's point out something here. If I have the function e to the j omega t, and I take the derivative of that with respect to time, well, it's a little bit hard to do this. We have e to essentially a constant times t. It's going to go e to the same constant times t times the derivative of what's inside. And again, j omega is constant from t is going to be j omega here. So what this tells you is that the derivative is just going to multiply by j omega. So instead of having to take a derivative here, assuming that our input's in e to the j omega t, the derivative is just going to be multiplying by j omega times the original input voltage here. I don't want to say it here. Maybe I'll just do it as, A angle phi e to the j omega t. So what we're doing is by turning, adding on this imaginary part, turning it into an e to the j omega t, whose derivative gets you back to what you started with, which is by multiplying by j omega. What we get from that is we can turn differential equations into algebra equations where their algebra has complex numbers, unfortunately, but it does make it so there's no longer differential equations. So what we're going to see in the next videos is we're going to say, okay, well, how can I apply this to a circuit as a whole? And what we're going to be able to do is we're going to be able to take these circuits, these RLC circuits, and we're going to, instead of having to write differential equations, we can just use entirely algebra to solve them. The only hang-up is the algebra is going to be algebra with imaginary numbers involved.